Chan Patil from Arts, Science and Commerce College, Mokhada, and I'm going to deliver one small lecture on Riemann integration using the image slideshow. It is similar to the PowerPoint. The only difference is there are images uh, that you have to show. So you have to just click on that image slideshow and then you have to choose the files, that is image files obviously, that you want to add, and you can rearrange this one. Here it is, you can see that start to, you can do up and down by using these arrow keys. So click on OK. Yeah. So but you can see that it is moving automatically, so I will change the settings, that is properties, and I will click on manual. Yeah, so now it will not move on its own. So yeah, click on OK. I have to assign some hotkeys to move forward and backward these slides, you can say. So you have to go to setting, files, and click on settings, and here it is hotkeys. So you can go to image slideshow, and here it is next slide. So you just press to right arrow key from the keyboard to move forward and press left arrow key to move backward. Yeah, and then click on OK. So now look at this. Now you can see it is moving forward and backward. Yeah, fine. So this is about the this OBS software. Now let's start. Let's begin our topic, that is Riemann integration. So basically, the what to mean by, first of all, Riemann integration by using graphical representation. Now you can see that. Look at this diagram graph. You can say this is the function f of x, y equal to f of x. Then what is the integration? Basically is the area under the curve in the given region. So here it is, say this is the a comma b. In between this a comma b there is a area, shaded portion is this one. Yeah, you can see that. And there are some this the parts, this area has been divided into some parts, you can see. So I'll tell you that later what do you mean by this one. So let's moving towards the, first of all, the definition of upper and lower Riemann sum. I will not go for the directly what is Riemann integration, but we need some basic terms. So we will start with this upper and lower Riemann sum. Yeah, so let's have this one. So consider uh, this uh, function f of x b, which is the bounded function in the given interval ab you can say 0 comma 1 2 comma 3 like that. And consider, let again this p be the partition of ab. Yeah, so see how is the partition p is the partition. The partition means these are the numbers, that is these are the real numbers, it is a set of real numbers x, a, x1 x2, xr minus 1 xr, and b you can see here, over here the partition of ab you can see over here. This is the partition of ab. Yeah, have you understood that what I mean by actual may the partition of ab? The interval AB is divided into some n number of intervals, sub intervals, you can say. You can see that this a comma x1 is sub interval, x1 comma x2 is the another second subinterval, x2 comma x3 is the another subinterval, like that. Yeah, fine. So let, so like that, let IR is equal to xr minus 1 comma xr be subinterval, that is the in general subinterval. You can see over here, you can see that, look at this. Yeah, subinterval. And let mr, small mr and capital mr be the infimum and supremum of the function f of x. Now what do you mean by infimum and what do you mean by supremum? Infimum of the function means the lower bound, first of all, which is the greatest one, that is also called as greatest lower bound. And the supremum means the upper bound, but which is the least one, that is the least upper bound means the supremum of the given function in each subinterval. Yeah, in each subinterval we have to consider mr and capital mr. Now I'll not go into the detail of this infimum and supremum right now. So you just let's continue this one. Let again this delta xr is equal to xr minus 1 be the length of the each subinterval. You know how to calculate the length of the subinterval. You know that suppose if you consider this x1 comma x2 as a subinterval, then the length of the subinterval will be x2 minus x1, or you can say x3 minus x2, like that. Yeah, so this is in general term, that is a delta xr with the length of the subinterval. Then now we will define this lower Riemann sum and upper Riemann sum. So the lower Riemann sum given by LPF is sorry for this one, this is LPF actually, the printing mistake is there. So LPF, and it is equal to summation small mr and multiply by delta xr, sum of this all small mr's and delta xr. Yeah, and what do you mean by upper Riemann sum? Here it is again, the printing mistake is there. Here it is UPF, it is denoted by UPF is equal to summation capital MR delta XR. So you can uh, now look at this. Yeah, now suppose this is the function y equal to f of x. Here it is, this is the suppose function. I will show you this one. Yeah, so how it looks, that upper Riemann sum and lower Riemann sum, if you can see that this is the partition, this partition. Yeah, 1 2 3 4 and 5. Yeah, this given function, and this is a given function y equal to f of x, and this is the a comma b. Say you can see that here it is 0 and 1. Yeah, so your interval is 0 comma 1, that is ab, you can say a is 0 and b is 1, and your function is this y equal to f of x is bounded by this 0 comma 1, and this a comma b, or you can say 0 comma 1, is partitioned into 5 sub intervals. Yeah, you can see that there, here it is 0 to point 2, point 2 to point 4. Yeah, so what we mean by upper Riemann sum is this area. Yeah, you can see that this area, you just partition this one like this. Yeah, and this is the extra region, you can say this one. You can observe this is the extra region. So uh, that is the, this is about upper Riemann sum. And lower Riemann sum, it is the same thing. This is the your region, sorry, this is your function y equal to f of x, and between the 0 comma 1, it is again the same partition is used in 5 parts, you can say. And lower Riemann sum looks like this. Look at this is the lesser part, you can see that, this one, this is, you can say the lower Riemann sum. So have you understood the how that looks like, that upper Riemann sum and lower Riemann sum? Yeah, now if I partition the same AB, or you can say same interval 0 comma 1, here it is, into say some more parts, that is say 10 parts. Yeah, suppose say 10 parts. Now here it was the given interval was divided, partition into 5 parts, but here it is say in 10th parts, I think so, into 3 4 5 6 7 8 9 10. Yes, it is partition into 10 parts, then what will happen? You can see, you can observe that this portion, this extra portion is little lesser than this, the previous one. You can see that here it is, the, you can say, the bigger part, you can say. Yeah, and you can observe that this is the lesser part, and here also, here also, lower Riemann sum. Yeah, and if you partition this one into now more, yeah, more sub intervals like this. Now I think this is not 10, but this may be 20, or yeah, like that. So n equal to 20, suppose, say this. So you can see that this upper Riemann sum, the area, yeah, extra area was there, right? So it is now reduced. You can see that reduced, but as compared to this one. Yeah, you can see that. And also the lower sum, it is coming, you can observe that it is coming towards the this function. Yeah, I'll show you in the next slide. Look at this, look at this. Yeah, it is the combined one. So this was the first slide, you can say. This was the second slide. Yeah, the region, just look at the regions. And this was the third slide. Yeah, so this is the upper and lower Riemann sum. Yeah, with the number of subintervals, say n equal to 5, 10, 50. I think it was a 50, yeah, of equal subintervals with the equal length. So now I will define what I mean by upper and lower integrals, Riemann integral. So upper Riemann integral means it is denoted by UF, integral a to b bar, actually here, or upper integral fx is the actually the infimum of function f of x, such that x belongs to xn minus 1 xn, and the lower Riemann integral is denoted by lf, is equal to actually the supremum of f of x, supremum of f of x, such that x belongs to xn minus 1 xn. Actually here I missed out this one. Actually it is infimum of UPF, actually. Yeah, infimum of UPF, such that x belongs to xn minus 1 xn, and supremum of LPF, such that x belongs to this. So yeah, so this is the example. Say f of x equal to x square, then how to solve the example using that. First of all, you have to find the partition of given interval. Then you have to find the supremum and infimum in the given subintervals, and then you have to find upper and lower Riemann sum, and then you have to take the limit as n tends to infinity. That is nothing but taking the infimum, or you can say supremum. So if they are equal, then you will say that the function is Riemann integrable. I forgot to tell you that if UF is equal to LF, then the function is said to be Riemann integrable over AB. So thank you.